Chapter 2, End-to-End Machine Learning Project. In this chapter, we are going to work on machine learning project from start to finish. Here are main steps I will follow. First, get the data. Second, explore and visualize the data to gain insights. Third, train-test data separation. We will compare various separation methods, start from building it from scratch, then exploring random sampling, and compare with stratified sampling. Fourth, prepare the data for ML algorithms. This includes cleaning the data, scaling it with transformer and data pipelines. 5. Find a suitable model and train it. 6. Fine-tune the model using hyperparameter optimization to avoid overfitting. 7. Launch, monitor, and maintain the system. To keep this video short, I will cover only the first 4 parts. Our task is to predict the median house value using various attributes. Let's start by loading the data. With this code, we have loaded the data into Pandas DataFrame, which is a table-like structure that makes it easy to inspect and manipulate data. By using the head function, we can quickly take a look at the first few rows of the dataset. From info function, we can see the most columns are the type of floats, except for the ocean proximity column, which is an object type representing category data. Also note that total bedroom column has some missing values. We will deal with these missing values during the data preparation step. It's worth mentioning that using double brackets on DataFrame returns another DataFrame, while using single bracket returns Pandas series. A DataFrame contains both row numbers and column names, whereas the NumPy series only contains a series of data. The HIST method is a great way to visualize the data. It allows us to easily observe the mean, max, and the most frequent values for each numerical attribute. It can only display numerical data and cannot use to visualize category data, such as the ocean proximity column. After visualizing our data, we now have a first impression of it. Before moving on to the next step, let's create a test set and put it aside. The reason we separate the test set at this stage is because the test set serves as a real-world, unseen data. We want to ensure that test data remains completely untouched during the entire process so that we can obtain unbiased generalization errors during the test phase. There are several ways to create a test set. Here is a simple implementation. The shuffled indices contain randomly shuffled values ranging from 0 to the length of the data frame minus 1. The test set is created by selecting the subset of the index from 0 to length of the data frame multiplied by the test ratio, while the train set consists of the remaining index. The problem with this approach is that every time we run the program, we get a completely different subset due to the randomness of the permutation. We need to ensure that results remain consistent across the different runs. One way to achieve this is by specifying a seed value in a NumPy random function. This ensures that the permutation function generates the same order of indices on each run, making the process reproducible. We can use the Sklearn library to achieve the same goal. This will produce the same result as mentioned above. Now let's discuss the fourth approach. The previous method doesn't work well for a dataset that is constantly updated with new instance. When a new instance is added to the data frame, the permutation will generate a completely different random set. To resolve the issue, we can use the hash of the data frame's row identifier to separate the train and test sets. Since the hash value for the same row will always remain consistent, Newly added instance will not affect previous generated train and test sets. Here is how it works. We are going to use row number as an identifier. Create a data frame with resetIndex method. The crc32 hash function hashes the input into a 32-bit number. The hash is evenly distributed. We can place an index into the test set if the hash value is less than 2 to the power of 32 times the ratio. So far, we split the train and test sets using a pure randomly approach. However, this method will introduce bias, especially when the dataset contains imbalanced subgroups. To mitigate this issue, we should use stratified sampling. Let's use an example to explain stratified sampling. In the US population, 51.3% are male and 48.7% are females. When creating a train and test set, we want to ensure that these proportions are preserved. Stratified sampling achieves this by dividing the data into homogeneous subgroups called strata, and then sampling from each subgroup in proportion to its size. This ensures that both training and test sets remain representative of the overall population. In our case, we can apply stratified sampling by dividing the dataset into subgroups based on the median income categories and ensure that each subgroup is proportionally represented in both training and test sets. This approach helps reduce bias and ensure that our model is trained and evaluated on data that accurately reflects the real-world distribution. Here's the code to transform the continuous median income value into categorical values. We'll add a new column called income cat, where the median income values will be grouped into a specific ranges. For example, values from 0 to 1.5 will be labeled as 1, values from 1.5 to 3 will be labeled as 2, and so on. Now we can stratify the data based on the proportion of each subgroup. Stratified shuffle split in Sklearn library helps us accomplish this. Set n splits equal to 1 will produce one training set and one test set, while n splits equals to 2 will create two pairs of training and test sets. We'll verify the stratification by checking the value counts. The proportions in the training and test set will be roughly the same as the overall dataset. Now we have well stratified the training and test set. We can remove the income cat column after the stratification. The next step is data cleaning for the training set. Let's assign the features and labels into two different variables. We will use them from this point onward. Let's first handle the total bedroom column. We can isolate this column to a data frame, total bedroom, and use the info to check the data. It contains some non-values. A common way to handle missing data is to substitute all missing data with either median or mean of existing values. The median is generally preferred over the mean because it's less sensitive to outliers. We can use a simple imputer to perform this substitution. Here's the code. By initializing simple imputer with strategy set to median, and then calling fit and transform on the data frame, we can replace all the non-values in the total bedroom column with its median value. Since the returned result is numpy array, we can use Pandas function to convert it back to a data frame. Let's examine the distribution of total bedroom using a histogram. We can observe that it has a very long tail, which is not ideal for machine learning algorithms. Machine learning algorithms generally perform better with well-distributed data. To address this, we can use a function transformer to apply a logarithm transformation to each value. The steps are similar to simple imputer. The transformer takes a data frame, applies logarithm transformation, and outputs a numpy array. Then we can convert this array back to Pandas DataFrame. The code is pretty much like simple imputer, except combine fit and transform into one function, fit transform. After this transformation, the distribution turns into a bell-shaped distribution. The center of this total bedroom is around 6. We notice that many columns use different scales. For example, the number of rooms has a much larger range compared to the income. Without feature scaling, machine learning algorithms might focus on the number of rooms and ignore median income. To ensure all attributes on the same scale, we can use two common methods: min-max scaling or standardization. Min-max scaling, also called normalization, shifts and scales value to a range between 0 and 1. However, it is highly sensitive to outliers. For instance, if most data lies between 0 and 40, but there is an outlier with a value of 100, the scaling will compress all the values into a narrow range, which is not ideal. Standardization, on the other hand, is less affected by the outliers. It subtracts the mean value and divides the result by the standard deviation. Unlike min-max scale, it does not restrict the values into a specific range. Let's apply standardization to the total bedroom data frame. We will use standard scalar to transform the dataset's value using the standardization formula. The standard scalar will first subtract each value with a mean and divide the standard deviation. After the transformation, the data will be centered at 0. Great! We finally completed cleaning and feature scaling for the total bedroom column. To summarize, we filled in the missing values with simple imputer. We have transformed the distribution into a bell-shaped distribution with the function transformer. We standardize the data using standardized scalar, and the data is distributed around 0. If we repeat this step for all other columns, it will involve a lot of repeated work. Fortunately, Sklearn provides a pipeline to streamline the process. We can stack all the transformers into a pipeline and let it handle the transformers together. Let's rewrite the above 3 steps using a pipeline. We'll create a log pipeline with 3 transformers and use the pipeline to fit and transform the data frame. The final result will be identical to the 3-step process we followed earlier. This approach is not only efficient, but also makes the code cleaner and easier applied to other columns. Let's get back to the data. Consider the columns total room and households. If we combine the 2 columns, we can create a new feature, rooms per household. This new feature is more meaningful than the original column because it provides insight for the average number of rooms per household. A household with more rooms might indicate a larger or more expensive house. This approach isn't limited to just these 2 columns. We can create other meaningful features by combining addition columns, such as population per household, divide population by households, bedroom per room, dividing total bedroom by total rooms. To implement this, let's write the code and perform column-wise transformations. We will use a function transformer to create a custom function that divides the first column by the second column. The lambda function is a division. After we apply this transformation, we will obtain a well-distributed room per household column. Next, let's clean and transform the ocean proximate column. This column contains categorical data, which means we need to encode it into a numerical value for machine learning model to process it effectively. One approach is to assign each category a number, such as 1 to 5, to represent different categories. However, this method has a significant drawback. A model might misinterpret the numerical values as having ordinary relationships. For example, it might assume that a category labeled 2 is exactly halfway between 1 and 3, which is not meaningful for ocean proximity since the categories are not ordered. To address this issue, we can use one-hot encoder. This encoder creates one binary attributes column for each category. Since there are 5 categories in ocean proximity column, one-hot encoder will create 5 binary columns. For each row, only one of these columns will be 1, indicating the category, and the rest will be 0. This approach avoids the misinterpretation of ordinary relationship between categories. Similar to the pipelines we used earlier, we will include a simple imputer to handle missing values. Even though the current data frame doesn't contain any missing values, it is good practice to include this step. We never know what the data look like in the future. After that, we will use one-hot encoder to transform the categorical column into a binary matrix. By default, the output is a sparse matrix to save memory. We can convert to a dense matrix with toArray method to inspect the results. Now we have explored the log pipeline and the categorical pipeline. Let's move to the next step. The latitude and longitude columns. These columns contain geographical coordinates, and we want to transform them into a format that can be used effectively by the machine learning models. A common approach is to cluster the coordinates based on the similarity measurements, where each value represents the similarity to the cluster center. We can use a clustering algorithm, such as k-means, to transform the latitude and longitude into cluster-based features. Before applying the clustering algorithm, let's visualize the latitude and longitude data. The data forms a shape resembling California. From the visualization, we can roughly estimate there are around 10 distinct cluster centers. Sklearn doesn't provide a built-in transformer for this specific task, so we need to create a custom transformer. Here's how we can implement it. We create a custom transformer class, cluster similarity transformer, which uses a k-mean algorithm to cluster the latitude and longitude of the data. Then feed method trains the k-mean model on the input data. The transform method calculates the similarity between each data point and the cluster centers. The getFeatureNamesOut method generates meaningful column names for the output. It is useful to generating data frame. The k-mean algorithm will fit on the input. After training, the cluster centers will be accessed through the cluster center attribute. The transform function uses RBF. The transform function uses RBF to calculate the similarity between the input X and the cluster centers. Let's fit our transformer on the latitude and longitude data. The output shows the closest cluster center for each latitude and longitude pair. We can verify the column names using the getFeatureNamesOut function. After transformation, the coordinates are converted into an array of 10 numbers, where each number represents the similarity to a specific cluster center. After all the preparation, let's put the code together and make the final transformer to transform all the training data. The column transformer includes all pipelines and transforms each column corresponding to each pipeline. This is one default pipeline added for any columns not mentioned, such as house median age in the data frame. We have now completed the entire data preprocessing phase. The next step will start training a model. I have included the code into the GitHub link. Hope you have learned something today and see you next time.